Okay, welcome everyone to my continuation of what is algebraic graph theory. I would like to wrap up now the story about random graphs with colorings, which is kind of very, very different from the previous video. We're going to recall what we have seen in the previous video, but it's kind of the same. It's kind of the same story, and then really different in some sense. So it should be the same type of theorem. Kind of makes sense to be the same type of theorem. I will comment on that later on, as in the previous video. But somehow it's way more difficult to prove. And I will just show you what I think, or what I've just looked up. It should be somehow the state of the art, up to some fluctuations because I'm not an expert. So there might be some improvements. I'm following a book which is about 10 years old. So obviously, there might be some improvements. But as far as I could tell, the problem is really difficult. So maybe they're just not. And just I tell you what I think is the state of the art. Okay, colorings is the following problem. So here's a graph, and we are also always considering those graphs, and we will color them with, well, colors. And we do that in a way that neighbors in the graph, so here, as those three neighbors, they all need to get different colors. This is somehow a bad example. So if this is red, these can't be red. That they are all blue is kind of a coincidence. So let's have a look at this one. It has this neighbor, and this neighbor, and as you can see, they all have different colors. Okay, so a coloring is just give your vertices a color such that neighbors need different colors. And the chromatic number, which I will denote by chi, yes, is just the minimal number of colors needed for a color. So of course you can have like many colorings, and the natural question is to minimize that problem. So what is the minimal number of colors needed? And that's our number here that we want to compute, and it's called the chromatic number. And usually computing this number is like terribly difficult. It's really horrible. It's bad. It's really difficult. I will comment on that later because I tried it with a machine, and essentially the problem didn't finish. The computation was too difficult. But anyway, this is really difficult. So what can we say about our favorite random graphs? The coin flip graphs, remember, this just means n vertices and probability a half to put an edge between two vertices. Really, it's just really flipping a coin for each pair of vertices and put an edge with probability, a coin flip, so probability a half. So what can we say about this case for this terribly difficult problem of computing the minimal number of colors needed? A priori, it's not so clear, but we had like in the previous 10 videos or whatever, it looked like we can actually say a lot about random graphs. So maybe you have some chance of saying something about this number. And whenever I see such a problem, I'm trying to put that into some machine. We'll see that on the next slide. But it turns out that this seemingly innocent question, which looks very similar to what we have seen in the previous 10 videos, was really open for a long time. And even a simplified version of it was open for decades. And not because people didn't try. People tried very hard. Very smart people tried very hard. It's somehow a very difficult problem. And I kind of want to rephrase the problem a little bit to make it a bit easier. So can we find, instead of computing that number explicitly, which is really difficult, can we do something a little bit easier? Can we find like an asymptote, like this picture here, right? So the function here is quite difficult, but the asymptotic is quite easy. It's just the identity line x equals y. So maybe we can't write it down in an explicit formula. Maybe we can just do it for very large n approximately, right? That's what I'm asking here. And even this question was really like open for decades and without much progress, which is a bit surprising because we have seen very similar questions in the previous videos and they were fabulous results. But somehow here for the coloring, it gets really terribly difficult. So let's have a look what we should expect. And as I said, I would put this problem just into Mathematica. So what is done here, so I have 250 random graphs with 50 or 60 vertices. If you compare that to the previous video, I did something like 10,000 graphs for way bigger number of vertices. But this one wasn't compiling, or this one wasn't running, because the calculation of those numbers is so terribly difficult. But anyway, you still get a pretty good picture of what's going on here. So for chi, so 250 of our random graphs with 50 or 60 vertices. So here's 50 and here's 60. You can essentially see what happens. So for 50, there are some fluctuations. They're like a really tiny and completely number that they completely ignore. But otherwise, they're just two, namely 9 and 10. So the chromatic number is essentially always 9 or 10. And very similar for 60, the chromatic number. So this is a really strange scaling because there are only two numbers that turn up, is 10 or 11. So for all graphs, with all 250 graphs, there was not a single one that had something different than 10 or 11. So the answer is somehow pretty clear what we want. It just feed it in a machine. The machine will tell you there will be a concentration, and you can actually somehow, if you would do more calculations, guess roughly where the concentration will happen. Okay, so that's somehow very easy to get, and somehow you would conjecture that this is true, but it turns out that this is terribly difficult to prove. It's really not easy to see why, because in the previous video we essentially had the same, and then it was quite easy to prove. And here we see the same pattern, so it should be obviously, it should be obviously true. You can just feed in even more examples, but it's really, really difficult to prove. So there should be a concentration, but that's not quite what we can prove. So here's the formal statement. I would comment on that statement in a second. You can do that in complete generality, but let's ignore the complete generality here and just go for n and p. P is now any number, and there's something involved, but there's this funny number that I already said. So the number of colorings is roughly around this size, but there is an interval, and that's kind of the point. So here's our number, our leading number, but there's an interval where it can vary. And the interval is exactly the problem. So the function f is not really the problem here at all, but the length of the interval will be kind of a problem, which I will state at the next slide. So what we can prove, so this is the theorem, is that the number is concentrated in some interval, so this little interval here, which depends on n and p. And the problem is that clearly this interval is really, really tiny, like 2 points here, but we somehow can't prove that. So the interval, comment on that in a second, will actually get quite large. So what we can prove is that we essentially have the asymptotics that we would guess from the picture, but it's kind of stretched out over an interval, and the interval is, sadly, we can't prove that the interval is small. Which we were able to prove on all previous points, but here you can't. It obviously it is. You can just check it via a machine, but you can't prove that. So it's somehow still a really, really difficult problem. So let's have a look at the interval lengths. The interval lengths, depending on n, and of course I take p equals a half, which is my usual choice. So the interval length actually goes to infinity. So for graphs with 1,000 vertices, the interval length is around 33. Right? So for graphs with 1,000 vertices, we expect 1 or 2 as an integral length, but we can only prove that it's around 33, which is kind of really, really bad, right? So you really, everything says that the interval is tiny. It's really just concentrated around this number here, this one here, but we somehow can't prove that. We have this interval that we can't get rid of. And that's kind of a problem. The clique number, that's exactly what we had in the previous video. If you want to go back to that one, we have seen exactly the same phenomena. The approach was exactly the same, but we got a much better statement because the interval was really tiny in that case, or we were able to prove that the interval is really tiny. It's probably very tiny in this case as well, but we just can't prove that, which is somehow a bit disappointing. Okay, so that's kind of the state of the art. Random graphs and colorings, as far as I know. Certainly, you can play around with that, and potentially someone has improved the length of the interval. So what we would try is to prove that the interval is actually smaller and smaller and smaller and smaller, and hopefully you get eventually the statement that the interval only has 1 or 2 points or something. Integer points. So it should be really tiny, and the proof or the statement should be exactly the same as for everything else we have seen so far, but somehow here in this case, it gets so much trickier to prove. So at some point, in the whole story. There's a complexity jump, and this problem is just so much more difficult than all the others. Anyway, I hope you enjoyed the story about the random graph. We were actually able to say quite a lot about random graphs, which is a bit surprising. And random graph is just a model for almost all graphs. So for almost all graphs, even something like the chromatic number is reasonably easy to compute. Of course, we have this interval, which is a bit tricky, but it's of length 35 or 33, whatever it was, for 1,000 vertices. That's not so bad. It's just a bit disappointing. That's what I'm trying to say. It's still much better than trying to compute this funny number by hand or by a computer, which, well, okay, I could have done it in a smarter way, but my machine wasn't able to do much better than a few hundred vertices, computing this number for a few hundred vertices. But here you can say actually much more. And that's kind of the story I wanted to tell about random graphs. So to wrap up random graphs, a lot of properties about graphs are really difficult, but for almost all graphs, for the random graphs, they're actually not so difficult to compute. I hope that story was reasonably clear, and I hope you enjoyed that part. And next time, we will jump to a different part of algebraic graph theory. Anyway, I hope you enjoyed this video, and I also hope to see you next time.